So guys, welcome to our channel once again. We have here these 10 questions to answer on the topic electric fields. So guys, this will be about electric circuits. So in short, it's till the end of this video. Let's go ahead and start with the first question here, and that's question number 1. It says 6 dry cells, each of EMF 2.0 volts and internal resistance of 1.0 ohm are connected in parallel across a load of 3.0 ohms. Calculate the effective current in the circuit. So guys, in order for us to calculate the effective current in this circuit, we have to recall that E here is equal to I into R plus R. So this is the equation we are going to be using, but then E is already given to us here as 2.0 volts, and for these 6 circuits the voltage will remain the same since it's a parallel connection. So it means that the voltage is 2.0 across this. So whereas for the internal resistance, we are going to have R to be 1/6. That's for this, we're going to have 1/6, and that's 0.17 here. So in this case, R here, which is the load resistance, is going to be the 3.0 ohms. So now that we've gotten all these, we are just going to make I the subject of this equation, and then we'll get the effective current. So I here is going to be E over R plus R. So for this, we are going to have that E, which is 2.0 here, is this. So this will be 0.17 plus 3, and then I is going to be 2/3.17, right? And that's 0.63 amps. So that's option C here, guys, 0.63 amps. So that's the answer to this question. Let's go ahead and consider the next question, guys. So that's question number 2 here. So for the question number 2, it says the ammeter A2 in the circuit diagram above reads 3.0 amps. Determine the reading of the ammeter A1. So guys, this is actually very simple. So we know that the ammeter A2 and A1 are actually connected in parallel to each other. So this connection shows that this ammeter A1 and ammeter A2 are in parallel connection to each other, which means that the voltage here and the voltage here and the voltage here are the same. So in that case, let's recall that V is equal to IR. So it means that I1 R1 is equal to I2 R2. So in that case, I1 is the current on this ammeter, but it's not given, so we say it's A1 here, that's the ammeter 1, then times 6 ohms here. This will be equal to I2, which is 3 amps, times 4 ohms. So A1 here, if we make it the subject of this equation, will be 3 times 4, that's 12/6. So this will be 2. So the answer to this question is option A, and that's 2 amps. So let's go ahead and consider the next question, guys. So that's question number 3. It says a circuit contains 3 ammeters, A1, A2 and A3, with readings of A2 and A3 shown as indicated in the diagram above. Determine the reading of A1. So we've seen the reading of A3 here, which is 5 amps, and we've seen that of A1, which is not given, and then A2 is 2A, 2 amps. So guys, if the current should flow this way, of course it will actually get here as 5 amps, then move towards here. So let's notice that the current will split this way and then get to A2 and then A1. So in order to consider what the current getting to A1 and A2 will be, it means that A3 will be equal to A1 plus A2. So in that case, A3, which is 5 amps, will be equal to A1, which is unknown, plus A2, which is 2 amps. So guys, in this case, A1 will be 5 minus 2, which is 3 amps. So that's option A here, guys. That's option A. And that's the answer to this question. So let's go ahead and consider the next question, guys. So that's question number 4 here. It says, which of the following actions will not increase the sensitivity of a moving coil galvanometer? So we have increasing the area and the number of turns of the coil, B, using a light pointer, C, using a weak hairspring, D, using a strong temporary magnet. So guys, the answer to this question is option B, and that's using a light pointer. So let's go ahead and consider the next question, guys. So question number 5 here says, a moving coil galvanometer which gives a full scale deflection with 0.005, and that's the current here, is converted to a voltmeter reading up to 5 volts. So this is supposed to be 5 volts, using an estimated resistance of 975 ohms. So we are to actually calculate the resistance of the galvanometer here. So looking at the options here, we have 250 ohms, 25 ohms, 2.5 ohms, and 0.25 ohms. So here, what we are going to do is, first of all, we'll note that since this is a series connection, actually when we convert a moving coil galvanometer to a voltmeter, we do that by making a series connection between the galvanometer and a multiplier. The multiplier here is a high value resistance. So let's take note that this connection will always be in series. So since it's in series, the voltage across this will be the sum of the individual voltages. So that's the voltage for R and the voltage for the galvanometer. So whereas the current will be the same across here. So let's also recall that V is equal to IR. So if V is equal to IR, we can replace each of these with the individual currents and voltage for each of them. So in that case, the voltage reading here is already given to be 5, right? So we have that 5 volts is equal to the IR for this resistance will be the current, which is 0.005, then times the resistance of the resistor, which is 975 ohms. So this is 975 ohms, and then this will be added to the current times resistance. That's V for G now is the current times the resistance of the galvanometer. So we have 0.005 times the resistance of the galvanometer. Actually here is not given, and that's what we are looking for. So we are going to write it as RG So in this case, we are going to multiply this out, and then we have this. So let's go ahead and do this here. We have 5 is equal to 0.005 times 975. That will give us 4.875, and then this will be plus 0.005 times RG. So this 0.005 times resistance of the galvanometer. Now, to make RG the subject of this equation, we are going to have that RG is equal to 5 minus this. So 5 minus 4.875, then over the coefficient of RG, which is 0.005. So this will be 0.125 over 0.005. So in that case, RG is going to be, when you divide this, you're going to have 25. So that's 25.00 ohms here, and that's option B here. So guys, that's the answer to this question. So let's go ahead and consider the next question, guys. So that's question number 6 here. It says the circuit above illustrates a standard resistor R, voltage source E, and lamp L connected in series. If the temperature of R is increased, the brightness of the lamp will A. increase sharply, B. remain the same, C. increase gradually, D. decrease slightly. So guys, for this illustration here, let's take note that an increase in temperature will actually mean an increase in resistance, or will lead to an increase in resistance in any way. So if an increase in temperature leads to an increase in resistance, that translates to an opposition to the flow of the current here. And guys, when there is an opposition to the flow of the current here, it means that the brightness of the lamp will decrease, and that's option D here. So guys, let's go ahead and consider the next question. So that's question number 7 here. It says, in the wiring of houses, the fuse is connected to the wire colored A, yellow and green, B, brown, C, blue, D, yellow. So guys, the answer to this question is option B, and that's brown. So let's go ahead and consider the next question. So that's question number 8 here. It says, a student wishes to measure a potential difference across a resistor R. She has a galvanometer G and some connecting wires. What else does she need? We have A, high value resistor connected in series with G. So guys, obviously the answer to this question is A here already. When you want to make a voltmeter from a galvanometer, you actually need a high value resistor, and it will be connected in series with the galvanometer. And that's it for this question, guys. Let's go ahead and consider the next question. So that's question number 9 here. It says, which of the following statements are not true of a moving coil milliammeter? So guys, this moving coil milliammeter is the galvanometer, and we have options here. I says it can be used to measure alternating currents. II, it has a linear scale. III, it can be adapted to read higher values of current. IV, a resistor connected in parallel with the milliammeter will convert it to voltmeter. So guys, here actually we are looking for the options that are not true for the moving coil milliammeter. Actually, I here says it can be used to measure alternating current, but that's false, guys, because it cannot measure alternating current since the alternating current is rapidly changing direction. So, but option II here is true for this, and option III is also true for this, but then option IV here is not so true, because in order to make a voltmeter from this milliammeter, we have to connect it in series with a high value resistor and not in parallel. In that case, the answer to this question is option C, that's I and IV. So let's go ahead and consider the next and last question, guys. So that's question number 10 here. It says a circuit is set up as shown in the diagram above. When the key is closed, the reading on the ammeter will be. Alright guys, let's go ahead and calculate for this together. Now first of all, if we want to get the reading on this ammeter, we have to understand this formula. V is equal to IR, right? And the I, which is the current here, will be equal to V over R. But then in order for us to get the total resistance here, we have to find the resistance for this parallel connection and then add it to that of this series connection in order to get the total resistance. So R for the parallel connection is going to be 1 over R for this is equal to 1 over R1 plus 1 over R2. So in this case, 1 over R for the parallel connection will be 1 over 1 plus 1 over 1. So guys, the LCM of 1 over 1 is 1, and then 1 here is 1, then times this is 1, then 1 here is 1, then times this is 1 again. So this will be 2 over 1. So if 1 over RP is 2 over 1, then RP is going to be 1 over 2. So you remember when you cross this, so 2 RP is 1, then RP is 1 over 2. So we're going to go ahead and wipe this here so we can have a space to solve for the total resistance. So the total resistance here is going to be the resistance plus the sum of this parallel resistance. So that's 1 here plus 1 over 2. So if I add this up together, I'll have 2 here. So this will be over 1, and this 2 over 1 is 2 times 1 is 2, and then plus 2 over 2 is 1 times 1. So I have 3 over 2 here. But then we are looking for the current. So current is voltage over the resistance. So the voltage here is 3, then the resistance is 3 over 2. So for this, I can bring up these 2 here in order to remove the fraction here from this denominator. So I'll have 3 times 2 over 3. So 3 goes for 3, and then I'll have 2 amps. So guys, the answer to this question is option C here, and that's 2 amps. So guys, this is where we'll end this video for today. If you enjoyed this lesson, please give it a thumbs up. Don't forget to subscribe to this channel if you're not a subscriber. Also, if you have any specific question regarding this video, you can drop the question on the comment section below, and we'll be sure to give you a response. So finally guys, we want to encourage you to join our YouTube channel community. Thank you once again for watching this video, and see you on the next one.